Hello, welcome to Multivariable Calculus, and today we are going to start talking about vectors. Now, the first question is, well, of course, what is a vector? Now, we talked about these in your Cal 1 and Cal 2 courses, but today we're going to be spending a little bit more in this unit and throughout multivariable, we're going to be spending a lot of time with vectors, so it's good that we kind of get to know just exactly what is a vector. Now, you're always going to find the same basic definition for a vector. It always consists of the same two parts, magnitude and direction. A perfect example of this would be velocity from your physics course. Now, velocity, it has direction and length. For example, we would say we're traveling like 5 miles per hour uh, at 210 degrees east, south, east. Notice we have our magnitude, how fast we're traveling, and we have the direction in which we're going. Now we also can see velocity last year in pre-cal written as a vector, and we'll get to this in a second. Something like 1 comma 5. Well, this is a velocity. If I were to graph it as from calculus last year, we're going right 1, up 5. I now know the direction in which we are heading, and if I find the length, I can find the true speed. But more on that later. Okay, so and that's what kind of goes along right here, that a great way to represent vectors is velocity, because again, we saw these last year in BC Calculus, or your Cal 1 or Cal 2 class in college. So let's take a look at the following velocity vector below. We're given the vector v hat as -2, 5. Now, last year we talked about these symbols. These symbols are what we call chevrons. You can use parentheses to talk about vectors, but it's more accurate to use these chevrons. And there's another form we're going to talk about later on as well. From last year, we learned that we learned that the change in the x value here is -2, and the change in the y value is 5. We can almost think of the velocity vector like slope. So if I think about a vector, I can think of this as the first one. There's my change in x, and there's our change in y. There's our change in x. There's our change in y. Now you might ask, well, why do we do this? Well, this is for two-dimensional. I can think of slope as change in y over change in x. But why would we want to write it using our vector form or our chevron? Well, when we get to three-dimensional graphs, we're going to add another variable. You can have your change in your horizontal, of course, your change in your vertical, change in horizontal, change in vertical. But now we have to add another one, our change in our z-axis, or the change in the height of it. And it's really hard to write our slope, in air quotes, you can't see me, but I'm making air quote, our slope using our traditional model. So we do prefer to write them in our chevron form. So let's talk about how we graph it, of course. Let's kind of review this. So we can think of vectors like slopes. Let's take a look at the graph below. Here we are, we have our starting point. Now, we are not told where we are starting in this case right here, and that's okay. We're not always told where we start. We're just told the direction which we're heading. We're told we are heading left 2. That's what that -2 stands for right here. And we are traveling then up 5, +5. Our change in y was -2, and our change in x was -2, and our change in y was 5. So very important that we talk about starting points right now. If I just tell you how fast you're going, how fast you need to go, and the direction, that's really not going to tell you where you're going to wind up. We typically need a starting point, some place to start. Now, if we start at the origin, we have a special name for it. That's called the component form of our vector. Again, more on that in just a few minutes. Now, from this vector, we can find the direction and the length. Now, again, we're going to talk about how to find the length more later, but the direction we're going to talk about for right now. However, this vector does not tell us any information about where we are starting. Therefore, any vector with the same length and direction are what we consider the same vector. Matter of fact, because they're the same vector and they have the same direction, these are considered parallel vectors. And we have a bunch right here. Note, each of these vectors, they're all going left 2, up 5. Every single one of them. Left 2, up 5. Left 2, up 5. Left 2, up 5. All of these vectors have the exact same slope and as well as the exact same length. Of course, to get the length, you kind of figured out how to get the length, just Pythagorean theorem probably by now. But they're not starting in the same spot. But even though they're not starting in the same spot, we say that all of these vectors are the same. We just don't have a starting spot yet. So let's talk about how we can represent vectors. Now, there are 3 ways we can represent the vector. We will use the first 2 quite often in class. The first one is what we talked about last year in BC. Normally, we like to use chevrons. This is what we use in Calculus BC or your Cal 1, Cal 2 course in college. And this is just right here. This is just saying this is our change in x and our change in y, followed by chevrons. Another form, or another way we call it, is linear form. Now, linear form is very neat. If you're in physics, you might have seen this before, maybe not. It just depends. And we use the letters I and J. We're going to spend some time in a couple of days talking about what I and J represent. But just to kind of give an idea, I is what we call the unit length in the x direction, where J is the unit length in the y direction. So, same thing. So we could write, so in linear form, it would be delta x I. We put a hat on it because it's a vector. It's a unit length vector plus 5. Whoops, sorry, not 5. That's silly. There we go. Our change in y, delta y, in the j direction right there. And that's our linear form. Very easy to do. Now, what is a unit length? We're going to talk about that, but a unit length is just something that is 1 unit long. That's it. Whatever unit you're in, it could be 1 foot. It's like a mile per hour sort of thing. Now, the third way is to use matrices. This you'll talk more in your linear algebra course. And we do see these quite a lot because they're easy to do some algebraic operations like multiplying and doing some other things with matrices, with vectors. So if you have to multiply 2 vectors together, this is a really nice way to do it. And again, of course, you can see there's your delta x, there's your delta y, and you can go either direction, like so. All right, so that's the end of part 1. Go to part 2. We're going to take a look at some more examples and some applications of vectors. I'll see you then.